Okay guys, welcome back. I'm going to help you with Lab 2. And like I said, just like last time, let me zoom in here. I'm going to go through the mechanics, so I might not necessarily answer, let me highlight, not necessarily going to answer all these parts of the lab for you, but I'll show you how to produce, for example, the mean, the median, the standard deviation right here. Okay, so for starters, it says for this example, you will use the data tab baseball 1 from the file project which I gave you. The file contains 2004 salaries for 2 Major League Baseball teams. Column 1 has the salaries for a randomly selected American League team, and column 2 for a randomly selected National League team. So for part A, we have to calculate the mean, median, and standard deviation for the salaries for keywords each team. So let's start there. I'm going to pull up Excel here. Okay. So you see, if I zoom in here, you can see down at the bottom it says baseball. So this is, and then up top, Red Sox and Mets. Okay. Column 1 and column 2 respectively. Okay, now I want to get Megastat up and running on here. So I'm going to hit pause a second. So I don't know if you can see this little tab right here. Oops, let me get my pen. Up top, it says, up top where it says add-ins. So when you attach Megastat, you should have a little tab right here that says add-ins, and that's where we're going to use Megastat to make our lives easy to find all these descriptive statistics. Okay, so I'm going to go to add-ins. And you can see, you can't see me pressing the button, but you can see the tab highlighted right there. So add-ins, Megastat. I'm going to go down to descriptives. And then it asked me, what do I want? So in that problem, it said we want the mean and the standard deviation. I don't think it asked for anything else. Well, you can always take these for starters. Input range. So I'm going to highlight just the Red Sox, and I'm going to hit OK. See, and so it produces, and then what you could even do is, stylistically you can copy paste this into Word or whatever, but let's just kind of highlight here. It has the name, the Red Sox, so mean, it's reporting the mean, which is over 4 million some. And notice it's reporting the standard dev, the standard deviation of the salaries, which that's a very large standard deviation, right? $5 million some for standard deviation. Okay, so again, that's for the Red Sox. When there's such a large standard deviation like that, it leads you to believe that maybe there's outliers in the data. Okay. Now, I'm going to go back, add-ins, Megastat. And let's see if it'll let me zoom in there. Again, descriptives, but this time I'm going to highlight input range. I'm going to highlight the Mets. So now I'll highlight all the Mets data. And take all those descriptives and hit OK. Aha. Now I'm just going to write on here. Notice that the mean, notice that the mean for the Mets was less, right? 3 million some. Notice that the standard deviation was also less. So note to self, the mean was less than the Red Sox, and the standard dev was also less. So again, we're retrieving important information directly from Excel. Okay, now let's go back to the actual project. Oh, I forgot to mention that the project asked for the median as well, and that's something I wanted to highlight here. I don't want to say too much to give it away, but notice, and we talked about this in class, notice that the median salary is only $900,000. Well, hey, $900,000, that's significantly less than the mean. So notice that the mean salary is 177. Okay? So we had said something in class about when the mean is greater than the median, sort of significantly like that. Okay? And skew, we mentioned something about skew, or possibility of outliers. Okay, let's go back to the project now. Okay, so I'm just going to highlight here. So for part A, calculate the mean, median, and standard deviation of the salaries. We did that. And then it says, which measure of central tendency, the mean or the median, do you think gives a more accurate picture of the salaries? And write an explanation. I'm going to give you a hint. When there's skew in your data, you're supposed to report what? So which measure is more resistant to outliers, the mean or the median? So I'll give you another hint. If you Google, if you do a Google search for NBA salaries or NFL salaries, you'll see what they report on those websites. They always report the median. The median's more resistant to outliers. So it's going to give you, if one guy's making a whole lot more than everybody else, then, hey, let's report the median salary and not the mean. Okay? C, use means, medians, and standard deviations of the two sets to compare the two teams and include comments on similarities and differences in salaries. So I'll let you do that. That part's creative. Now, for number 2, we got some mechanics here. It says to open the baseball data and construct a stem and leaf display of that and describe the shape of the distribution. Okay, so I'm right back into the same baseball data, the same file, and I want some stem and leaf plots. So again, megastat, descriptives, and notice, now what I'm going to do, since we already had all the other information, I'm just going to go ahead and just click stem and leaf plot alone. Okay. Input range. Well, we can do it for the Mets a while, since Mets is already highlighted. And hit OK. Okay, so I have a stem and leaf for the Mets, which I could have chosen. It probably would have been prettier to pick a split stem here. Let's take a look. Let's go back megastat. Oh, let me be back on the data set. Let's go megastat, descriptives. Okay, input range. This time I'm going to highlight the Red Sox. And this time I'm going to check split stem and hit OK. Okay, so now we're getting a feel. You can tell, even if you superimpose, and let's see if it'll let me do this. The beauty of a stem and leaf is that it preserves the data. Oops, let me use my red pen. Preserves the data while simultaneously giving you the shape of the distribution. So if you kind of tilt your head to the right, you'll see the shape of the distribution is like this, right? So that's skewed right. Tail is to the right. And we kind of knew that anyway, because remember, we saw the mean was significantly greater than the median. So now we're just sort of verifying that with our stem and leaf. And actually, let me go back and do another split stem for the other team. So descriptives, input range for the Mets, because their stem and leaf didn't look that great. And you guys are going to be copy-pasting this into Word, so... okay, so I have split stem checked there, and hit OK. Yeah, that looks a little better. So now that's for the Mets. And like I said, for you guys, you can literally, right-click. Notice how I'm highlighting, right-click, hit copy, and then paste that whole entity into Word. Okay? But they're both right skew. So even if I highlight on here, and you can even illustrate that too, still right skew. So for both of those teams, we witnessed that. Okay? Okay, so for Part B, I pretty much answered that for you. It says, not for Part B, for Part A. It says describe the shape of the distribution of the salaries, after you've basically constructed your stem and leaf. So we did that. Then in Part B, it says calculate X bar plus or minus 2 standard deviations, and then use the appropriate rule, the empirical rule or Chebyshev's rule, to make a statement about the percentage of players. About the percentage of players' salaries, that should be a an apostrophe there, players' salaries that you would expect to fall within this interval. Well, I'll give you a hint. Empirical rule is for bell-shaped data. So this data isn't bell-shaped, right? Chebyshev's rule is for any data set. Chebyshev's rule. So we'll use that. You recall, you might have to dig up in your notes what that means, Chebyshev's rule. But let's, for starters, just calculate the interval x bar plus or minus 2 standard deviations. And I believe that was for each team. Yeah, calculate this and use the appropriate rule and make a statement about the percentage of players you expect to fall in that interval. Yeah, so you would do that, it should say that there, but you would do it with regard to both teams. So you can actually just go back to your output sheet on Excel, and you can just go back and retrieve the critical information for both the Red Sox and the Mets. And here you might have to stretch the width of your column there. So, okay, so for example, so you're just retrieving nothing fancy. You're just retrieving this information from your descriptive statistics. So basically, x bar plus or minus 2 standard devs, okay? So your mean, so you're just going to calculate, okay, 4243283. You can just go ahead and round to the nearest dollar. Plus or minus 2 times the standard dev, which was 5 million some. You know, 5,324,000. So 2, I'm just going to write here, plus or minus 2 standard devs. Now you'd actually have to perform that calculation. You could do it like right within Excel, or you could just use a calculator and state it. But the thing is, 2 standard deviations, what does Chebyshev say about that? And I'll give you a hint. Chebyshev says that 1 minus 1 over k squared percent, at least 1 minus 1 over k squared percent must lie within 2 standard, must lie within k deviations of the mean. So k is the number of deviations of the mean you're looking at. So 2 devs, 2 standard deviations of the mean. So you're actually going to plug, note to self, you're actually going to plug 2 in for k. Okay, well 2 squared's 4, and 1 over 4 is, 0.25, so 1 minus 0.25, you're looking about 75%. So Chebyshev says that at least 75% must lie within 2 standard deviations of the mean. Then you can actually calculate, is it true? Do at least 75% of the players lie within 2 standard deviations of the mean? You can actually tally that, okay? And let me use my eraser here. Likewise, so basically you would get those bounds for the Mets, and then you would get those bounds for the Red Sox as well. So for both teams. So, okay, so for the Mets, if I'm calculating that interval, x bar plus or minus 2 standard deviations, you can see the Mets mean was 3 million some, so 3452178, and then plus or minus 2 times the standard deviation, and again, I'm just retrieving this standard deviation right here, the 4728817. So the standard deviation is huge, right? 4 million some. Okay? But anyway, you would crunch out that interval, and you would basically get a lower bound and an upper bound for which 75% of the data is supposed to lie within, according to Chebyshev's theorem. Okay? At least 75% of the data. All right, so now, like I said, you can literally type this out and just, or you can command Excel to do it, or you just type it out and write it on your paper. Okay? So again, for part B here, where it says calculate the interval x bar plus or minus 2 standard deviations and use the appropriate rule. Now you know it's Chebyshev's rule, and then it says comment on the percentage of players' salaries that you would expect to lie within those bounds. So I kind of gave that away, so you should be able to get that. In part C, suppose you're interested in determining how well the highest paid player is relative to the rest of the players on the team. For each team, convert all the players' salaries into standardized scores, Z-scores, and locate the highest paid player from each team. So basically, you list the highest AL salary and its Z-score, and the highest National League salary and its Z-score. So the big thing is you have to remember that Z equals X minus mu over sigma. Now this you do not want to do brute force, by hand for each team. You want to write a little command here in Excel that's going to make your life easier. So I'll show you how to do that. Okay, so I hope you can see what I've done here. I got the z-score for the first. So what I did is I went up here and I wrote Red Sox. And then if you look in my command window in my formula bar up here, and I'll highlight this. Let's see if it'll let me write on here. Right here. You want to see what I wrote, right? I commanded it to take A2, which is basically this number right here, minus the mean divided by the standard deviation, which is exactly what you're supposed to do, right? X minus the mean divided by the standard deviation is, that's how you get a z-score. So I retrieved the mean and the standard deviation from, and I'll just show you, I went back to the output sheet here and, retrieved the mean from here and retrieved the standard deviation from here and literally just typed in the command. Okay, now the beauty of writing that command, when you write the command for the first cell, like, this observation, so it computes the z-score, but the beauty of that is if you just click and drag from the right corner on down, it should continue that type of pattern and compute all the z-scores for every single one of these observations here. So again, I just went to the bottom right corner of that cell and clicked and dragged it all the way down. And now what that does is that enables the eyeball to very quickly see which observation had the largest z-score. So big note to self, because that's what we're supposed to report, right? So largest z-score was, and you could see that anyway. I mean, take a look at that salary right there. Okay? So that means that person was making a lot more than everybody else, right? Because their z-score is 3.4, which means they're 3.4 standard deviations above the mean. So, okay? So they're making a lot more relative to the rest of the players on their team. Let's put it that way. This person here is also making a lot more too, 2.5 standard deviations above the mean. Some of these people with the negative z-scores, right, they're making less than the mean. All right? Now I'll do this with you so you can see how to write a command. So you can see I'm up here in the formula bar. When you write a command, you do the equal sign, right? And then now I'm going to go and try to do the Mets. So I want this first, B2 minus, now let me go and retrieve the mean of the Mets. So I'll go back to my output sheet. The mean of the Mets was this number here, 3452178. So I'm actually going to type that in. See how I'm typing in up here? 3452178. I'm rounding. And then I'm going to close that off in parentheses. Oops. Let me hit pause. Just a little glitch there. So I've taken, B2 minus, the mean for the Mets, divided by, now let's go and retrieve the standard deviation of the Mets, which was, what was it, 4728817? So I'm literally going to type that in, 4728817. Okay, now if I go back to my baseball sheet, see, it produced the Z, there it is, there's the z-score for that particular, observation. And now again, you're used to that. Let's go to the bottom right corner, bottom right corner, click and drag all the way down till the last observation, of the Mets, which was, this observation. So again, what that does is it enables you to look for the Mets. And the largest z-score for the Mets was, your eye can quickly, scan down the list and see the largest z-score was 2.9. So, that player for the Mets right here, made a lot more money relative to the rest of their team. But still, they were only 2.9 standard deviations above the mean, whereas this guy here was 3.4 standard deviations above the mean. So let's go back to the actual project. So now I kind of gave away that explanation. So it said in part C, it said, list the highest AL salary and their z-score. We did. I showed you the z-scores. and the NL salary and the Z-score, and then compare the standardized scores for those two players and who is the higher paid one relative to the rest of their team. So we gave that away, the one with the higher Z-score. So I'll let you report on that. Okay, and then we just have one more problem to go, which is number 3. And for this example, we'll be using the college data set, which is on the second tab of your Excel file, and it contains verbal and math SAT scores. Okay, I'm going to hit pause there. Okay, so here you can see I've pulled up the math and verbal SAT scores, and I'm just highlighting here. See this tab down here, it says College 1. Okay, so let me revisit the project description and see what we need to do. I think we need to make histograms for starters. Okay, so I'm going to highlight, it says to open the data tab, College 1, which we did, and construct a histogram for the math SAT scores. And then it says describe, and part B, describe the shape of the distribution. So let's just go ahead and sort of knock out part A and B here in one shot. Okay, so just to remind you, you're going to go to Megastat, you're going to go to frequency distribution, quantitative, input range. I'm going to highlight the math SAT scores. I forget, pretty many students there. And you can just go ahead, it says histogram is clicked here, we can keep that. Go ahead and hit OK. Ignore that error message. Okay. So ignore the error message. If I page down, it should have put it, there it is. Okay, and on top of that, it titles it down here. Let's see if I can zoom in. So you'll see it titled it, so it reminds you, it's nice, you don't have to do it yourself, it reminds you that that's the distribution for the math SAT scores. And you can see what you could say about that is it's fairly symmetric, fairly bell-shaped, which is what we know to be true about the SAT scores. They tend to follow the bell curve, so to speak. And you can also see, without actually calculating the mean, you can see that the center of the distribution is about the 550 range, somewhere along there, somewhere between 540 and 560 for the average SAT. Okay. Now let's actually produce the descriptive statistics, which I think is in the next question. So in part C, right here, it says calculate the mean and standard deviation of the math scores. Like I said, those are descriptive statistics. So I'm going to hit escape here and go back in. So to do that, remember we're just going to go to Megastat, descriptives, and we want the mean and the standard deviation. Okay. Input range, it should be on the correct data set when you do that. So, input range, again, right now it's dancing around my verbal scores. I don't want that, right? I want the math scores. So just make sure you're highlighting the right data set. We'll highlight those. And I have stem and leaf. I'm going to unclick that and hit OK. Now I'm going to scoot this. For some odd reason, Megastat, it kind of hides things underneath. So I had to scoot that histogram over. And you'll notice here it's producing those descriptors. So it's saying that the mean is about 548, which we had guessed, and the mean score was 548, and the sample standard dev was 36.77. Okay, now let's see what the next part asks. Okay, in the next part, in part D, it asks us to calculate the intervals, and that, by the way, that should have said X bar. That just, I guess when I pasted into Word, it didn't happen. But calculate the intervals X bar plus or minus 1 standard deviation, X bar plus or minus 2 standard deviations, and X bar plus or minus 3 standard deviations. And what percent of the data would you expect to fall within these intervals? So basically, X bar plus or minus 1 standard deviation. I'm just going to give this away. If it's bell-shaped data, which it is, then you're going to be going according to the empirical rule, right? So the empirical rule, remember that's the 68, 95, 99.7 law. So 68% of the data should lie between plus or minus 1 standard dev. 95% of the observations should lie between plus or minus 2 standard deviations of the mean. And so that's a 95. And then 99.7, or approximately all of the observations, should lie within plus or minus 3 standard deviations of the mean. Okay? So now to actually calculate these intervals, what you can do is do kind of what we did earlier. You can go back into your output and you can literally calculate. And like I said, you don't have to do the calculation on Excel. You can do it just with a handheld calculator. So you can grab the mean, 548.28, plus or minus 1 standard deviation. So your standard deviation is 36.77. You can literally compute that interval, the bounds on that. So bound 1, comma, bound 2. So you're literally going to type in 548.28 plus 36.77, and then 548.28, minus 36.77. And, if you like, you could probably just type that up here, 548, I'm just going to say 0.3, rounded, plus 36.77. Oops, I'll put it equals here. Actually, I should have make sure you're in the, here. You hit pause. So basically, when you're, if you're typing it into Excel, just make sure you're in one of the actual cells on your spreadsheet. So 548.3 plus 36.77. And then, likewise, for the next one, 548.3 minus 36.77. Okay, so there you have your bounds, and over here you can just remind yourself, plus or minus 1 standard dev, okay? So you can just remind yourself what that stands for. So basically, long story short, we got the bounds here for plus or minus 1 standard dev. So according to the empirical rule, I'm just going to give you a push, 68% of all observations, so should lie within those bounds, 511 and 585. And what you could do is you could physically tally, how many of these observations actually lie within those bounds. Is it close to 68%? And I think that's what you're asked to do later on in the lab. Okay, and last but not least, so I didn't compute all 3 intervals for you there, but you understand how to do it now. So, the mean plus or minus 1 standard dev, the mean plus or minus 2 standard devs, and the mean plus or minus 3 standard devs, you would compute all 3 of those intervals. So I did the first one for you. And then in Part E, organize the data set into numerical order, and what percent of the data actually did lie within the mean plus or minus 2 standard deviations. So according to the empirical rule, 95% of the data is supposed to lie within 2 standard devs. So how close is it? So, and then it says to actually list the data points that did not lie in the interval. So how many did not? So you first have to compute that interval and then physically count how many but fell in that interval. And it's easier to organize the data in numerical order first. So that's really the part that I wanted to show you. So Excel has this nice feature where if you want to sort your data from smallest to largest, you can come over here and then you can go over to the sort and filter, and it'll say over here from smallest to largest. And that will help you decide, okay, how many of those observations actually fell within, the critical bounds that I'm looking for. It'll help you decipher. Okay? So now you'll see my data sorted from smallest to largest under the math scores. Okay? If I zoom in there, you can see that. Okay, so I think that once you've sorted the data from smallest to largest, and you've organized it, what percent of the data lie between and plus or minus 2 standard deviations of the mean, and list those data points that did not lie in the interval. I think you'll be able to do that on your own. And then part F, compare the means and standard deviations of the math and verbal SAT scores. On average, on which of the 2 parts of the SAT do the students do better, and which set of scores has more variability? Well, let's just go back and take a look at what we have so far. I'll go to the output. See, we have the descriptive statistics for the math. Okay? So I'm just going to, record here. The mean for math is about 548. But the standard dev is sample standard dev is about 36.77, right? Now let's just go ahead and do it for the verbal group of SAT scores. So again, your add-ins, I'm going to hit add-ins, I'm going to go to Megastat, I'm going to go to descriptives, I want the mean and the standard deviation, but this time input range, verbal group, verbal scores. Okay. Hit OK. And now, what do we see? We see, aha, the mean verbal score is a little bit more, right? 578, but it's got a standard dev 52.48. So although the mean is higher, how about the measure of spread, meaning the dispersion? So let me page back and compare that for you. So the sample standard dev is smaller for the math scores than it is for the verbal. So mention that. Okay, I hope that helps, and good luck with Project 2.